Okay, welcome back to some more atomic theory in room 405 with Mrs. Walton. I hope y'all did well on this. First, you were supposed to check if they were ionic or covalent and then practice naming them. So you should have figured out the first one was ionic, and then when it's ionic, we don't care about numbers or prefixes, so you should have named this sodium carbonate. The second one was two nonmetals, which made it covalent. When it's covalent, we do care about that. So, about the numbers, that is. So we turn this into 2 di and 5 penta, and we change the ending of the second one. So we get diphosphorus pentoxide. And the third one, you should have figured out that this one was also covalent, and we only have one of the first ones, so we don't have to use mono. So this turns into nitrogen trihydride. Number 4, we're back to being ionic again, so we don't use our number prefixes. We just say what it is and change the ending, magnesium chloride. In number 5, it's once again here an ionic compound, so all we do is say cesium oxide or cesium oxide, depending on how you pronounce it. Number 6, you should have figured out was covalent, two nonmetals, and use your prefixes, but we don't have to use mono, so it's bromine pentachloride. Number 7 is a metal and a polyatomic ion, so that makes it ionic, and you should have figured out that this guy was silver phosphate. Number 8, we should have once again figured out it was ionic and determined that this was lithium acetate. If you got this next one right, then you really remember how to name compounds, because titanium is in the middle there. And because of that, he needs to have a parentheses with his oxidation number in it. So he turned into titanium 2 sulfide. And number 10 here was once again covalent and turned into oxygen difluoride. If you struggled with this, I really want you to go ask your teacher to practice some more naming with you. Okay, so let's move on to chemical reactions. If you remember, a chemical reaction always creates something new. In this case, we took some iron, combined it with some oxygen, and made iron oxide, which is rust. So on the left, we always have our reactants, and on the right, we always have our products. And a subscript is, remember that little teeny number? Both of those guys are, 3 subscripts there. What we have to do is balance our equations to find those coefficients that go out in front. And in order to do that, we do a rep. R stands for reactants, E stands for elements, P stands for products. And the approach we want to take here is counting how many are on each side and only changing the coefficients, not the subscripts, in order to make it work. So the first thing I actually like to do is go up here, okay, and put in a 1 in front of each element. Okay, so I'm going to write it in since it's acting weird. We want to put a 1 in front of each of these elements and compounds so that we remember that 1 is invisible, but it's there. So we have 1 iron. How many oxygens do we have over here? 2. On the right side, we have 2 irons and 3 oxygens. This is a great example because can we ever make this 3 by changing what's in front of it? We can't, because it multiplies, and we can't change that into a 3. So the first thing you want to do is go ahead and double that odd number. Well, how can we double our 3 by changing our coefficient? We can just turn our coefficient over here into a 2. And I'm going to erase this so you can see that 2. So we're turning that guy into a 2, but that changes a few things for us. It distributes in, and it changes my number of iron, which turns into a 4. And it also changes my number of oxygen, which turns into a 6. Now I can go to the left side and make some things work here. How am I going to get 4 irons on this side? Well, I'm just going to change my 1 over here into a 4. Erase my numbers. Okay, so that turned into a 4. So my table is going to change. Now this part of my table is happy. And I need to get 6 oxygens, so what should I put in front here? A 3. which will give me 6 oxygens. Now that my table matches up, everybody's happy. My equation is balanced, and I only changed my coefficients. Good. Okay, so why do we balance equations? We do this because matter cannot be created or destroyed. It can only turn into something new. This is the law of conservation of matter. Okay, so let me type that in here. Matter cannot be created or destroyed, but it can be transformed into something new, and that is the law of conservation of matter. When we want to balance something, we take inventory, figure out the amount we have on each side, add coefficients to balance them, and then look to see if we can simplify at the end. So keep that in mind as you're balancing equations. Okay, so then we have our reaction types. Y'all have been pretty good at this, so let's see if we remember. Single replacement is when someone comes in and kicks out somebody else. If somebody's lonely, it's single replacement. Combustion is when something explodes or creates a fire. It's not always an explosion, but it's fun to think of it that way. So if we're going to have fire, what do we have to have? We have to have oxygen. So water and carbon dioxide come out on the product side. And on the reactant side, okay, we have to have oxygen. So must have oxygen on the reactant side. Double replacement is when both compounds switch partners, so nobody's single. Synthesis is when there's only a plus on the left side, and they go together to make something new on the right side. Decomposition is when there's only a plus on the right side, one reactant being broken down into 2 products. If you're a really visual person, make sure you look at your foldable for this, because it breaks it down really well. And lastly, we have a neutralization reaction, which is when an acid and a base form salt and water and get back to that neutral pH. Remember what a neutral pH is. It's a pH of 7. Okay, so let's practice. What do you think this first one is? Well, there's a plus sign on the right and not on the left, so it must be something that is decomposing. In this next one, I have a single guy who comes over, kicks out somebody else, and makes him single. So that must be single replacement. In this one, I have a plus sign on both sides. This guy's single, but nobody's single on this side. It doesn't seem like it's matching up. I better consider combustion. I have oxygen on the left. I have carbon dioxide and water on the right. Must be a combustion reaction. Then I have these 2 guys on the left who are single coming together to make something that's lonely on the right side. All alone, no other plus signs. That one must be synthesis. Next I have hydrochloric acid and potassium hydroxide making potassium chloride and water. What happened here was one guy kicked out the other, but the other guy came back. Everybody's in a relationship, nobody's single. This isn't only a double replacement reaction, but it's also a neutralization reaction, because I have an acid, there's my H, and a base, my OH, and it made a salt and water. In my last one here, I have hydrosulfuric acid, sodium hydroxide, and they're switching partners, plus signs on both sides, nobody's single, so it must be a double replacement, and it's actually also a neutralization reaction because this is an acid and a base. So neutralization reactions are always double replacement reactions. Okay, awesome. So we made it through all those sections on reactions. Make sure you practice your reaction types. Make sure you practice balancing chemical equations, because those are really easy questions to get right on the final. We also need to make sure we're practicing naming both covalent and ionic bonds, because that's a super important subject to know. All right, keep studying hard, guys. We're almost there.